Cool. Hi, everyone. So I hope that you are as excited as I am today. So let me start with the survey. How many of you are using Node here? OK, keep your hands up, please. Keep your hands up. How many of you are using Node in Lambda functions? Not many. OK, that's good. Perfect. So it means that I have double the work to convince you to think about serverless. Perfect. So today we are going to cover one topic that I really love, because back in the days, believe it or not, I didn't have Air, but I was a developer. And I work a lot on embedded system, low-end devices, all the usual stuff that usually challenge the developer. Nowadays, with 10 cores Mac, usually it's easy to create 40,000 divs inside the DOM and everything works. Back in the days, or also in recent years, in low-end devices, it's slightly more challenging being a developer. And therefore, performance matters. And as you will see, performance matters not only for the challenge as a developer should have, but also for optimizing your applications. So my name is Luca. I'm a principal solution architect in AWS. I'm based in London, but despite that, I'm Italian. Today we are going to cover a lot of ground, and I want to give you a couple of highlights that sometimes are not easy to find, definitely are not in our documentation, but we have shared publicly a few of the insights behind the Lambda service. So let's start with the Lambda 100 that I think is the key part. Usually, you know, when you think about Lambda, people think, so, OK, so it's a black box, and we don't know how it works behind the scene. Perfect. Let's debunk this myth. So this is how it works behind the scenes. So you have, like, say, multiple services in AWS that could trigger a Lambda function. And what you see inside that nice rectangle with the top left corner, the Lambda service logo, this is everything that is abstracted for you. And when you are, let's say, polling some messages from a stream or from a queue, or there is a direct invocation, synchronous invocation from an API gateway, wherever, usually your code lives there. So all the rest of the part that you see are managed completely by AWS. Now, as you can see, there is a bit of stuff that are happening in the middle. And that front-end layer, for instance, is not the front-end as many people would think. It's just a front-end service that takes care about finding the right workers in the right region, in the right availability zone. Because bear in mind that Lambda has a very nice thing that you forget about the availability, because we take care about availability. So by default, when you deploy a Lambda in production, you have like multiple availability zone, usually free, where your Lambda function is up and running. If you decide to have a Lambda function that is VPC attached, and therefore is connected to a virtual private network, you can decide how many you want. You can have 1, you can have 3, you can have 5 in case that the region allows you. And this thing is enable you to really, let's say, think of what it matters. That is the code that you're writing for your applications. OK, there is another thing that you need to know before we start to drill down into the example. That is this one. This one is from the documentation, and I really like this sequence diagram because before joining AWS, I was an architect, and I love doing these kind of diagrams because they're very clear. People understand that very, very quickly. So there are two important phases that you need to bear in mind. That the one that we're going to improve today from an existing implementation of an API. That is the initialization phase. The initialization phase in Lambda works in this way. When you call an invocation of a Lambda function, and it's the first time that you are, let's say, calling that specific function, what we do is taking the code that you have written, taking the runtime that you selected, for instance, Node.js, we put everything together inside the sandbox, and we initialize that. You can have, as you can see, there is the extension initialization that think about a sort of sub-process that is running alongside the Lambda, that you can even create your own. There is the runtime initialization, and finally, there is your function initialization. That is the part that we are going to optimize today. There is basically called, that part is called once, only at the beginning of the creation of a sandbox. The second part that is very interesting is the invocation part. Every time that you have a sandbox up and running that is created by AWS, you're going to hit that sandbox multiple times. Therefore, what it means, the faster you respond to a request, multiple times can be reuse that sandbox. That, if you think about that, start to become very interesting. Because now it means that if we optimize our code, we can have more throughput inside our Lambda functions, and therefore it costs less. Okay, and then there is the shutdown, but that part is not taken into account. So these are the three phases. Sorry, I forgot about to show this part. So instead of being abstract and starting to talk about a lot of diagrams, wherever, I said, okay, let's try to do something that is more pragmatic. Let's take what I call an unoptimized solution that basically was a work that I have done with a colleague of mine in the US, and was saying, listen, what if we take, let's say, the most common NPM packages that are out there, and we build a very simple example that is this API here. It's like a CRUD API that is querying Postgres database, and that's what we built. So we have observability at the top with CloudWatch, X-Ray for distributed tracing. We use IAM for the security and tweaking the permission of our service. We have a parameter store for storing all the environment variables, stuff like that. And then we have finally at the bottom an API gateway that is exposing our Lambda function and our Lambda function that is running our Node.js code. And then we have our database. And usually, in our experience, a lot of people start looking. There are two architectures in Lambda function. The one that at the beginning is by default is x86. And that's where people usually start if for the first time they're using a Lambda function. So we tried to build this solution that was just querying. As I said, my colleague is from US, so we were querying a database for retrieving the NFL stadiums. Nothing too fancy, okay? So just a classic read on the side. So there are a couple of things that we usually recommend. First of all, if you're not familiar with Lambda, the Lambda has this concept of handler. The handler is the thing that is called every time. So every time that you invoke a Lambda function, this is what the code that is running there. But the code that is running instead an initialization phase, as I showed before, is everything that is outside the Lambda function. So usually we recommend that any connection that you made to a database, or you want to retrieve secrets, you want to retrieve parameters, or whatever it is, are outside the Lambda function. So that way they will live for the entire life cycle of the sandbox. Because you have to bear in mind that Lambda are ephemeral compute. And therefore, when it's finished after a certain period of time, we reclaim the sandbox and we spin up other sandbox for you. So in this case, for instance, we are retrieving the parameters that are needed in order to call our database outside our Lambda function. That basically is an HTTP connection behind the scene that is retrieving this information from another service that is parameter store, and off you go, you have what you need. But remember, if it's a connection to a database, if it's secrets or whatever, do that outside the handler. In the slide, I showed you that there is a database that were composed by two icons. One is the Aurora Postgres, that is the services running your service, but there is also RDS. RDS proxy. And RDS proxy is something that is that we have seen for a while, and even when I was customer of AWS, we struggled a lot for, let's say, creating the connection pool, because if you have to handle that, you need to think about the connection pool. If you're using DynamoDB, it's different because it's HTTP based, but in the case of Postgres, it's not, and therefore you have to build your own solution. Vast majority of the time, I was building, and even our customers were building like a database and a service that handles the connection pool, check what was available, and so on and so forth. So it was a lot of what we call undifferentiated heavy lifting. So we created RDS proxy that takes care about the connection pool, but more importantly, it helps also with the performance of your Lambda function, because it handles secrets, so you don't have to call a secret inside your Lambda function. Great. And secondly, it handles the certificates. That is another thing that with Node 20 available in Lambda, we removed by default inside the sandbox. That showed around slightly less than 10 milliseconds of initialization of your sandbox. That is great. You think maybe 10 milliseconds is nothing. The reality is a ton, especially because bear in mind that we run this service, or there are, let's say, plus 1 trillion of invocation of a Lambda function per month worldwide. So every millisecond matters, okay? The other thing that usually we recommend is that the smaller is your code that is loaded inside the Lambda function, the better it is. Why that? As I said before, what we do is taking your code and selecting the runtime that you decided to use, Python, Node, whatever, and we put them together inside a sandbox in order to run your code. So obviously, if your code is gigabyte, it will take longer to initialize and be in memory and start to work on that. So therefore, one thing that we usually recommend, meaning use ESBuild that is available by default on our infrastructure as code system, like CDK, like in this case. Available by default on our Perfect. And after that, you minify the code so that should be, let's say, more performant. Remember that if you want to use top level await, you need to use ESM for what concern Lambda functions. And last but not least, there are other configurations. This is one thing that and that's another thing that we usually recommend. We will talk more in a few slides. PowerTools. PowerTools is a library that was created by the community, and AWS took over and started to build on top of it for every single language. So we have currently PowerTools for Java, we have for C#, we have for Python, we have for TypeScript and general Node. And what it does is an opinionated way for handling observability. So you don't have every time to rethink, okay, how do I do structured logs? How I can integrate with CloudWatch? How can I use asynchronous communication with those services? We take care about that. It's open source. You can even contribute. You can check the code that is running, and so on and so forth. The other thing is, this one is by default available, the external modules. So in this case, basically, another trick is by default, or the AWS SDK, so the possibility to call multiple AWS services is available inside the sandbox. However, what we recommend is that you embed the SDK that you're using, or only the SDK that you're using. If you're using just, I don't know, for instance, parameter store, you embed the code into your bundle, because reading from memory is definitely faster than reading from disk. So that's very important. And very often people think, oh yeah, but I already have AWS that takes care about the SDK. Yes, but you are losing milliseconds that are valuable for your response time. That is not great. As I said, PowerTools is pretty easy. So the recommended implementation in Node is using MIDI. It's created by Luciano, that is a fantastic contributor on open source, and not only. And in this case, we are finding basically the tracer, logger metrics that you want. You have a bunch of configuration, pretty standard. The other thing that is interesting is that I can use PowerTools for handling distributed tracing. So one thing that is very important is when you are debugging for performance, you want to find the performance-specific action. You can create, using X-ray, what we call subsegments. And subsegments are nothing more than, say, the operation for reading on a database, for instance, is starting here and it ends there. And we take care of calculating the time that is happening that part, and you can see straight away into X-ray the time that took for a specific operation. You can, if you use classes, you can even use the decorator for handling that part, and we will take that every time that you call the authenticate, in this case, function, we are going to take care of taking the tracing on that part. Okay, usually those are the best practices we recommend, few of them at least, and people start to write the code and they start to it. So what we did, it was very simple. So we started to think about, okay, let's try how well will work if we create this API that has using Node.js, and we are using Artillery for doing the load testing. We tested from 45 seconds to up to 2 minutes, and we use from 20 virtual user to 100 virtual user, just to simulate a bit of traffic and see how our code performs. This, by the way, is something that we recommend. Load testing for serverless is extremely important, because it's slightly different from any other, let's say, solution that you're building. You can always, let's say, with containers, say, I can over-provision or whatever, but because Lambda functions are ephemeral, based on the traffic, it will respond and start to scale. So it's very important that you run real testing and load testing to understand how your system would behave, because you can discover a lot of things. One thing that you need to take into account is this concept of cold start. And cold start is nothing more than the initialization phase that I showed you before. So when we are pulling the code and the runtime, creating a sandbox for you, this is the cold start, because it takes slightly longer. And here you can find a query that is helpful for if you're using CloudWatch Insight to retrieve that information. OK, so first test. We did, in 10 seconds, a ramp to 20 requests per second, so from 0 to 20 requests per second. OK, so we're starting to ramp up. And then we started to hammer it on for 50 seconds or to 50 requests per second. That's what we have done, basically. So there are a bunch of interesting things. Oh, sorry, here. So the first thing is we had in the, let's say, how we describe this system is that we have 18 cold starts that you see at the top of the chart. And then if you're looking at P99, we are slightly over 2 seconds for the P99 response of our Lambda function or our API. And then we started to look into what we can optimize, right? So we said that we start to look into tracing. As you can see, there are few things that are tracing inside X-ray, but what we care about is the execution time, because we cannot handle anything else. So as you have seen, Lambda service does a lot for us. And what we care about is now what we can optimize on our code. So in this case, for instance, in this, let's say, Lambda function, we have a worst cold start that was 1 second 43. And the best one was 1.21. Bear in mind that we have usually seen that cold start is probably less than 3% of the entire, let's say, code that you have with Lambda functions. And very often people are afraid to say, OK, you have a Lambda function at cold start and will impact me. Let's talk about that. There are ways that we can you can solve even cold start quite easily with Lambda function, but in general, it's not impacting massively your workloads. Then you have like the execution of the warm start that is by default 95% usually of your responses. And warm start are like that. So in this case, the worst one was 228 milliseconds for replying back. So it means that the sandbox is there, is already available. We started to hammer it every time. And the best one was 167 milliseconds. That it might or might not be OK, but in general, 176 milliseconds to respond back to the service, a bit of latency because it has to go through API gateway and going back to the browser. But still, it seems that is good. But obviously, we challenge ourselves and say, OK, what can we do better? Second test is this one. So here, there is no ramp up. So everything is cold. We just hammer it, like simulating a spike into the system to see how the things are working. So in this case, we have way more cold start, 137. Because obviously, if you have a spike, it means that no sandbox are available out of the box unless you activate the provision concurrency. That is one of the tricks. And you start to hammer the service. So we need to spin up all the different sandboxes and start to respond back. When they are available, we just, let's say, serve the traffic normally. As you can see here, the P99 is over 4 seconds, because obviously we need to take into account a massive scale that is happening on the fly. So we were asking ourselves, OK, can we optimize what we have seen? Can we make better in a way that everyone could achieve it in their workloads? And the answer is yes. So let's try to improve the Lambda function. OK, so first, we start to look into the architecture. As you can see here, there are a few new icons. For instance, we have now Elastic Cache that basically is running, managed services is running Redis for us. And the idea is, OK, we are serving for reads, because usually an API is either read-heavy or write-heavy. In this case, it's a read-heavy API. So what we wanted to do is, OK, let's try to create a cache-aside pattern, and we use Redis for storing in memory for a certain period of time the response of our stadiums. How often the NFL stadiums are going to change in an hour? Probably not very often, or never. And therefore, we thought, OK, so we evict the cache after 10 minutes. And when the cache is evicted, we go back to Aurora. The other cool thing of Elastic Cache is this one. Because we are using Elastic Cache that is available for all the sandboxes in Lambda, it means that every single sandbox that is connecting to Redis will have all the data available there, so they don't have to go back to RDS every time, because you need to think multidimensionally, right? And in this case, we also changed the architecture to ARM. ARM is based on Graviton2. That is one of our, let's say, chipset that we have designed carefully in order to save money for our customer and energy. So usually you have an improvement of 20% of your performance vast majority of the time. So then now the function logic is, OK, first load the parameters, check if the cache is enabled. We load the data from the cache. If the data, the cache return, we basically return back the response. Otherwise, we go to the database. The other thing we notice is this. I was bundling with ES build, and the DRM, basically, it blew up to 1.6 meg for doing what we need to do. And what I discovered is that we were using SQLize, the most popular NPM package for dealing with Postgres. And it was 1.6 meg because it didn't allow me to do tree shaking. And then suddenly I found Postgres.js that is the bundle size reduced. It was even less than 246. This is the final bundle. It was 40 kilobytes when I changed exactly the same functionality using Postgres. So bundles, usually the bundles matter. Now, here on the Node.js function, again, minification, but also tree shaking. Now, another thing that often people are not doing is tree shaking. That code elimination is another important thing. We want to optimize our bundle size. There is a tool that is called Power Tuning, open source, developed by Alex Casalboni. He's a smart guy based in Como, now in Bologna, actually. Basically created this idea of testing the Lambda function with different configurations to see which is the sweet spot for cost and performance. So before we guesstimate the size, saying 128 megabyte is the minimum that you can have in a function. So we went, OK, let's pick 256 megabyte. And we guesstimate that. But as you can see from the top of there, the response time is 1.4 seconds for that, with a cost that is similar to 512, but the response time, that is the second, the bottom part of this diagram, so basically this part here. So we spend even slightly less than the 256, but the response time is considerably faster. So memory size matters. And that's another thing that you need to test deterministically and not guesstimating the thing. When we did in an optimization phase, we found the sweet spot of cost and performance here between 512 and 1 gigabyte of memory. That's one pretty cool thing that you can implement in your CI/CD as well. Then we think, OK, we want to load the secrets, the parameter in a different way. Instead of initializing that, we can load inside an extension. There is an extension that is developed by AWS that enables you to have the TTL of, the caching with setting up the TTL and a few other things of parameter store and secrets manager. And therefore, you don't have to think about that. You just need to call your in HTTP fashion, like as you can see here. Here we are. You can call with a fetch your extension and say, give me the parameters. It takes care about caching it, and if the cache is evicted and it's expired, it's going to fetch the data directly from the service. So it's completely transparent for you. You forget completely about that, but it's quite fast because now you don't have to make a call to every time to the service, but you have like an HTTP server available inside the sandbox. And remember to use the session token that is available inside the environment variable of your Lambda function. And this is how you pass it, basically. Now, second test with this optimization. Not much, as you can see, but we will see the difference. First of all, we move from 18 to 9 code starts. Big win. So similar pattern. We ramp up to 20 requests per second, then we started to hammer it. The P99 dropped drastically. I don't know if you have seen that. We were over 2 seconds, and now we are in a decent shape. Worst code start was 784 milliseconds, give or take. Best one was 557. We immediately say, OK, it's already halved the performance of the other one with small tweaks here and there. Second important thing is warm start. We move from hundreds of milliseconds to 73, and this is the worst. Do you guess what was the best? Someone want to guess how many milliseconds? Exactly. So as you have seen, let's say you don't have to work hard, you need to work smart. And that's why usually it's really great when you start to look into the details on how Lambda works. So in the second test, we have, instead of 130 something cold start, 9. Because now you have sandbox, but the sandbox responds extremely fast. And therefore, it can handle more requests per second. Because you don't have to think how many transactions per second, and every second I need to spin up a sandbox. Is how fast my sandbox can return back a response, and then I know how many TPS I can handle. So just a comparison with or without, between the optimize and optimize. On the average, this is basically what we are seeing: 268 and 16.5 milliseconds. It's quite a big thing. We also introduced the possibility to activate and deactivate cache on the optimized version. And as you can see, made a difference. The fact that we started to move into Redis and using in memory, that saved us 84 milliseconds, give or take. So what I showed you is that the Lambda function can be optimized up to, in this case, 56% in the cold start, but more importantly, 95% on the warm start. And warm start is, as I said before, more often, so 95% of the time you probably have a warm start in your APIs. But more importantly, the faster it is, the more you can squeeze in requests per second. But there is one more thing. Sorry, I'm an Apple fan, so what can I say? So there is another thing that so there was a colleague of mine based in Nordics that created this low latency runtime, custom runtime. It's called LLRT. It's open source, available on GitHub. So it's based on Rust and is running Quick.js. So you don't have the full compatibility of the Node ecosystem for now, but there is a lot of interest. Why that? Because offer 10x faster startup time, so cold start, and 2x overall lower costs compared to Lambda. As we said, the faster, the cheaper. Okay. There are some limitations, as I said. It doesn't support entirely all the functionality available on Node. But still, if you're interested, you can see there. Now, this is what you can see in the website. This is like LRT compared to Node 20, 128 megabyte, and we are doing a put on DynamoDB. So we're just writing. As you can see here, we have an interesting thing. P99 is 83 on execution time of the Lambda function, the top part of this number, 1.6 second on Node 20. But obviously, I want to believe what I see, and therefore, why not using it in production? So I created this sample. So we have an Amazon API gateway that is exposing a Lambda VPC attached that is talking with EFS, that is a system file network. And we are fetching basically some files, okay? So the response time for Node in a cold start was around 700 milliseconds. That is not bad at all, because in VPC attached means that we have to do a lot of networking magic that you don't see in order to have the Lambda function running and connecting to your VPC, but the Lambda function is running in AWS VPC. So it's not that the Lambda is inside your VPC, okay? But with LRT, exactly the same code, it didn't change a line of code. This is the response time. So potentially, if we apply the same thing that we have seen, all the optimization we have seen before, and LRT start to take, let's say, some twist and being embraced more, and you can contribute, obviously, you can have even better responses. So key takeaways is choose your library wisely. That for us was main takeaway. So we have seen before SQLize was not tree shakeable and brought a lot of code that wasn't needed inside the bundle. Use cache where possible, in-memory cache, Redis. There are plenty of ways that you can cache your system, even upfront if you're using API gateway cache or you're using a CDN. Absolutely, you can do that. You can optimize with extension, delegate the certain operations that are not needed to run every time, like, for instance, retrieving environment variables. And last but not least, bundle size matters. So think about that when you are handling. It's not, let's say, the smaller, the faster is your cold start, and also your code will run better. And remember, there is also LRT now. If you're interested to drill down into the code, it's open source, all available. This is the link where you can find an article that I wrote with my colleague Matt on how to improve the warm start speed by 95%. So what I described today is more in detail with code example and everything. And that's all I got. I hope that you enjoyed, and yeah, enjoy the rest of the conference.
Thank you, Luca. Oh, okay. Where are you going?
See
here for
okay,
the question.
Oh, sorry. I thought that I was late.
No.
Okay, cool.
No.
Perfect. Good.
Okay. Raise your hands if you have a question.
Too mind-blowing.
Yeah.
Go for it.
Wait a sec.
How's it going? Can't complain.
What's your name?
My name is Gonzalo. Small question, but you mentioned that the ARM architecture tends to be faster in your experiments.
Yes.
Then why isn't it maybe the default?
Yes, that's a question that we receive every time. No, it's fine. So there are certain decisions when you operate at the scale that Lambda operates. As I said, we are talking about a trillion of requests per second. That if you change by default behind the scene, something like that, it might cause some challenges behind the scene that you don't expect. Therefore, we need to be extremely careful. And I have a lot of respect for the team that is handling that part to understand what is the impact of a simple change of the architecture. Because even when we are, we recently had the possibility to pin your Node.js, let's say, runtime version in a Lambda function, because we have seen that when we are forcing certain behavior on updating minors sometimes or wherever, we break some code here and there, and it happens because they rely maybe on very old APIs, wherever. So we need to be very careful on wherever we say is default. So x86 was default since the beginning because there was only that one. And a few years later arrived ARM, but at the moment, yeah, there is no plan to set as by default. I tried even to change a few open APRs for changing some even templates that we have by default in some CLIs, and they told me no, because by default people knows better this library over that library. And the SPI performance were better on the other side, we continue to use that. So, yeah, we have one there.
I'm coming. What's your name?
I had a question about cold starts, which is an actual problem I'm facing right now. So you spoke about serverless. We are basically deploying APIs with serverless on Lambda, which means, sorry, we are deploying APIs with Lambda, basically with serverless, which means the bundle size cannot be really small. Okay. Also, we cannot always use cache in these cases. So we have a lot of problems with the cold starts. How can we address them in our case, since what you described does not really work for us?
I think we need to have maybe we can have a catch up, and you can explain me what you're doing right now, and I can we can start to look into that. Maybe how large is the memory size that you set inside your Lambda function? It's like memory size wise is like half gigabyte. Did you start, and what do you have like a database, I guess, that you are querying or stuff like that? Postgres. So it's similar. Do you use RDS proxy? Okay. And size-wise, you said half a gig. Okay. So we can. And did you try power tuning to see if you can have better performance if you increase the memory? That didn't change much. Okay. So
the first response for the API is like 2 to 3 seconds. Like that's a lot of time.
Okay.
Problem.
Yeah.
So
We can have a chat, and you can explain me better what you're doing there, because it's not, let's say, it's as simple as saying, oh, change this parameter and it will go super fast. That's not like going how it works. But we can discuss that, so you can explain me what you're doing, and yeah, we can even review the code if you have the code with you. And if I come up with something smart, more than happy to help you.
You got another job. You're on customer support.
That's what I do.
We have time if you want for other questions. No, really? Okay. Cool. So thank you, Luca.
You're welcome.
Again.